right, thank you so much, Nitsa and Ruth. That was a very engaging conversation and something that we really appreciate out here. So thank you very much. All right. Oh, wait a second. Is there something wrong with the title here? I mean, Llamas at ITC. That's kind of a little strange, but perhaps we do need a bit of a petting zoo to drive some comfort on this otherwise intense day. I think people are a little bit distracted, and I think that's a good thing. So Meta's global infrastructure is foundational to the technologies and services we offer to our global community every day. So Sriram Sankar is Director of Silicon Lifecycle Engineering at Meta, and there he leads teams that are responsible for the entire lifecycle of Meta AI silicon at scale. Previously, Sriram led teams that are responsible for hardware health and availability of the global compute storage AI server fleet at Meta. And prior to Meta, Sriram led the engineering organization responsible for server and data center infrastructure at GoDaddy. At Microsoft, Sriram was responsible for the technical strategy and architecture of Microsoft's global data center footprint. And Sriram has a master's and PhD in computer science from the University of Virginia with over 10 patents and more than 50 publications. His team's work on silent data corruptions has been featured in several media articles, including the New York Times and other prominent technical blogs, and actually right here at ITC. So allow me to welcome, I'm very proud to do so, my metamate, Sriram Sankar.
Thank you, Savita. Sorry, thanks. Hey, folks, good afternoon, and thank you, Savita, for an excellent and long introduction. I really enjoy being here. I feel like, ITC is a community that I can have a kindred spirit. I can talk to people and they go, yeah, silent data corruptions, right? So that's something that I really enjoy. So thank you for having me here. Today I'm going to be talking about AI, but I also talk about our journey, which took us here, and what we have to look for in the future. At Meta, I've had the distinct honor, or should I say the fortunate place of looking at every single silicon that has come into our fleet across last 8-9 years. CPU, DIMMs, GPUs, flash, storage. My teams have had the fortune really to look at all the issues. Some battle scars, the good, bad, and ugly, so to speak. So I speak with a lot of data and experience. But then recently I took on a role to support our custom silicon efforts, what we call MTIA, Meta's Training and Inference Accelerators. I'm excited about the opportunity because I get to work from the ground up and solve a lot of challenges that have plagued our community for a lot of years. So with that, when I was building this talk, I was talking to Manohar Palluri. He was here last year talking about AI, and he said, why don't you ask Meta AI about title and so on. I did one better. I asked Meta AI to tell me what I do at Meta. So this, I think, is a good, accurate representation of what I do at Meta. It's about herding llamas in the data center. But for people that don't know, Llama is our large language open source model. It has been downloaded 300+ million times. But there's a lot of things that go behind the scenes in making a large training model work, right? As part of my talk, I will cover that. But before I go into that, I wanted to give a notion of the scale. I say, how do we test for AI at hyperscale? But what is that scale, right? So Meta, as a company, as a huge consumer, or our user scale is tremendous, right? So we have close to 4 billion people that are using one of our products, Facebook, Instagram, Messenger, or WhatsApp, every month. We have 200 billion plus reels that run on Facebook and Instagram every day. We have 600 million plus conversations that happen between businesses and customers every day. So we have a huge surface, we have a huge customer base. And we need to really have a at-scale infrastructure to serve our application that serve these customers. So what does that look like? So we have data centers across the globe. These are distributed, large facilities that house hundreds of thousands of servers. These are global, and we have to run services in a distributed manner, in a reliable manner, to service our applications. So if you have not seen data centers or been in one before, data centers are multiple times the size of a football field, tens of football fields actually put together. This is just an aerial view of like some of our data centers. You see like, generators, even like an electrical, substation. You see like, one of the pictures is an air handling unit. These are pretty large. I've been in those rooms and you see that pressure, like kind of, going through when they are like cooling air inside the data centers. So all of these facilities house a lot of like components and servers in them. So components and servers, drives, systems, racks, they need to come together, networks. So this slide shows some pictures of our racks, one of our storage trays, one of our like network, like design that we submitted to OCP. All of these things need to work together at our scale, hundreds of thousands of servers, millions of them across our data centers, working together to serve our services globally. The other thing that we have also done is to submit all of our hardware designs to Open Compute project. So anything that we have built and deployed in our Facebook data centers, in Meta's data centers, we have submitted to Open Compute project. And we continue to do so. This just shows our journey from 2011 till 2023 across compute, storage, network, and also some AI systems in the recent past. So the best thing about this that I love is, like all of these, contain our partnerships with different manufacturers, different ODMs, different suppliers. We work with a lot of this community in making sure we are able to like build and deploy them in our data center. So given this scale, in this talk, I have three major areas that I'm going to cover. One is a topic that this community probably already knows, but I'm still going to cover it because I'm going to show some insight into how we developed our muscle to deal with silent data corruptions at our scale, and why is it important for AI applications to deal with this important problem. The second thing that I'm going to focus on is our challenges of the present. We are building large AI clusters to train our Llama models. What are some of the challenges we face, and why is testing incredibly important as we deploy these large clusters? And finally, I'm going to talk about testing for our future. We are building our own custom silicon that I mentioned. I'm going to talk about our MTIA, Meta's Training and Inference Accelerators, and what are some of the challenges, or what should we look for when we are thinking about years into the future. With that, silent data corruptions. This was probably before I started giving keynotes on this topic. I started building the slides and I said, 2 plus 2, everybody knows that it should be 4. But then silent data corruption happens when silently hardware returns an erroneous value, right? 2 plus 2 equal to 5. So when I started putting these slides together, my son, he was pretty young at that time, and then he came in and said, you cannot put this up in your talk. People are going to laugh at you, right? And he is right. He is right? But then that showed me an important thing. This was before our paper was published. This was public. But that showed me a very important thing. His expectation is not wrong. When you think about computing, even when programmers or software engineers think about computing, you think about giving a set of instructions to the computer and getting back accurate results. When your fundamental expectation of accuracy is not satisfied, you have a big problem, right? I'm not comparing, like my son's expectation, but I'm just saying as a community, different communities have expectation on the hardware community that we delivered accurate results back to them. So what are silent data corruptions? They are silent errors in silicon. They are very hard to detect. There are instances where it has gone undetected for days, months, years, right? There was an instance where we had to go look for a computed value in the archive system and trace back how it got computed to a wrong value. And it has significant impact to our services. Engineers across hardware, software, or production environments spend a lot of time trying to debug what went wrong when hardware doesn't have a clue about what went wrong. So when we initially started talking about this to some of our partners and vendors, there's a very common thing. Like, but wait, cosmic rays, everybody knows about this problem, soft errors, radiation, you're going to fit, bit flip, you're going to face some errors, like, don't worry about it, the industry knows about it, and so on, right? So yeah, they were maybe partly right, but then they were also absolutely, way off in magnitude on what we are seeing in the fleet, right? So typically, cosmic ray-induced falls, 1 in a million. And I said, okay, I accept it, what you're saying is right. So then what we did, we ordered a bunch of GM counters, sent it to our data centers, measured the radiation, did a different altitude, and looked at different correlations. And no, it's not 1 in a million, it's not cosmic ray-induced fault alone. We saw data corruptions that were 1 fault in 1,000 devices, right? And this is just a pictorial representation. If you're following the screen, on the right-hand side, when I put that up, you see some of the dots moving across our infrastructure. There is a dot on the left-hand side also, by the way. You just don't see it because it's 1 in a million, right? This is an important point to note, because when you have millions of devices in your fleet, you are going to end up seeing faults that happen at this magnitude, and that's what happened to us. This is something that was, unexpected to us, because we thought like what the industry thought, and we said, okay, this is new. We need to go figure out what the heck is happening, because this is something that is impacting our applications, right? So for us, it was a needle in a haystack kind of scenario. We were not able to understand where the problem was happening, which hardware it was happening at. And this is also very difficult for us, because we are looking at hundreds of thousands across servers across our data centers. And this keeps moving about. The size of our infrastructure is growing, which is a very diverse, very varied infrastructure. And we needed to pinpoint this needle in a haystack problem. So we said, okay, we need help. We went to our vendors. And again, I'm talking about the journey to show you an important point, right? When we see signals, when we call for help, and we say, hey, it is just one-off issue, it is a manufacturing defect, it is there. This was a turning point for us. I remember clearly that instance where I said, to my team, okay, what does it take? What does it take to kind of pinpoint that needle in that haystack, right? So we started building infrastructure. We started building test methodologies to go figure out that problem. So because without that, we knew something was happening. We knew something was happening in our fleet, but we are not able to isolate. We are not able to pinpoint the reason or where it was happening. So this is an example that we published in our first paper on this topic. There's another story that I'll come to for the first paper we published, but this case study is probably familiar with the folks in this audience as well. So this is about Spark database, where we are doing a simple compression, decompression kind of function. And when you try to do the decompression, you call Scala's math.power function, and it tries to compute 1.1 to the power 53. When it does that, there is unfortunately or fortunately for us, because this was the turnaround, it was scheduled on a particular defective core and a defective CPU. And the result was 0. Again, I say the unfortunate, fortunate part, right? It is fortunate that the result was 0, because the code has a logic to check if the result was 0, then you don't write the rows into the database, right? It's a very common way people build code, so you don't want to only for non-zero values you end up writing into the database. And in this, there were missing rows. And our application stack had that instrumentation to check for it. That's another important thing, right? If Meta did not build the instrumentation across its stack, we wouldn't have been able to find this issue as well. So a bunch of things came together to show us how a silent data corruption was propagating up the application stack, and a set of instrumentation, days of debug from all of our teams figured out that this was actually a silicon defect, it's a hardware problem, right? So what does it take for us to go, isolate this fault though, right? This is the engineering effort behind the scenes to go tackle something like silent data corruption. So when things are written in a very high-level distributed language, you're not able to easily debug it to a specific instance, a specific core, a specific CPU. So you need to break it down into something that can instrument things for you. You can profile things. You need to break it into something that is manageable. You can put some checkpoints in and so on. So we got it down to 400,000 lines of assembly. Still a lot, because it's no mean task to go through, look at assembly line level reproduction. But that was still not enough. We needed to kind of weed out what we didn't need, prune a lot of stuff. We have to do a lot of best practices at getting down to a very, very scalable, very, very simple reproducer, and which we did. we went from a highly distributed application level debug down to like assembly level, from 100,000 lines of code to like 60-line reproducer. Why? Because one of our vendors said that they didn't believe that it was silent data corruption, it was some like random defect. That again is the turning point. That forced us to go down this testing methodology of building directed test. And we said, okay, we're not just going to give you the defective part. We're going to give you the defective part and the simplest reproducer in like 60 lines of assembly code. So, go run it, go figure it out, and tell us where the issue is, right? But it doesn't stop there, right? Because there is continuously, we are managing a large fleet. There is going to be continuously these kind of, once we knew that this was there, we needed to figure out how to scale it, right? How to figure out where else this could be happening. So from one silent data corruption, we needed to move to hundreds of them in our fleet. So we needed to like really scale our approach. Again, no such infrastructure existed, no such methodology existed for us. So we needed to build everything from scratch. This is something we take seriously. At Meta, we have a lot of like ownership across the stack. We try to like kind of not just say, hey, we found this one issue here, take it over and then go. We try to like build it into a systemic way to like scale it, and we also share it back with the community. Again, these are all papers that we have published. So, but going back to why was this a hard problem? Why is scaling? Why is detecting silent data corruptions a hard problem? If everything was just 60-line assembly code, you ran it, and you're all done, then we are done, right? But there is a lot of data randomization. Something that can work for a set of operands doesn't work for another set of operands. Something that can work for a specific set of electrical variation doesn't work for another. Something that can run in one data center at different temperature humidity parameters doesn't work for another data center. And there is also something that we tested now versus tested 6 months later, we might fail for a data corruption. All of these led us to like kind of not have approaches which is on the failure path, but approaches that needs to run continuously. And when I say continuously, we largely bucket it into two different aspects. One is run in non-production state, which is when we are not serving application traffic. Another, which is extremely hard to do, is to co-locate it with applications. Think about, these are all destructive tests. What I mean by that is it's actually going and testing something in a functional block or a particular instruction sequence in your CPU. So necessarily you're going to impact some kind of performance. So we have to do it in a very well-orchestrated manner and a very well-scheduled manner. And so we built two methodologies, Fleet Scanner and Ripple, which we call them, to go look at them. The idea behind them is very simple, right? So the Fleet Scanner, execution is hard. The idea behind them is simple. The Fleet Scanner is more like a pit stop approach, right? So when you have, when you're running a race, when you're like delivering, services to our customers, you need to take pit stops in the middle to do some maintenance, maybe firmware upgrades, maybe repairs, maybe like kernel upgrades and so on. So you have some amount of like downtime where you can run directed tests to detect whether there are silent data corruptions. So that is the first methodology. So we have done huge amount of stride in this methodology. Initially, when we were talking about this, it used to take us 6 months to converge on our fleet size. We have reduced it to 1.5 months. Remember that this is opportunistic testing. So there is, like only when there are events like that, we are able to like test for these in our fleet. But we have more than 110 billion, fleet seconds of test time. This is significant test time. I cannot underscore how important this was in identifying data corruptions in our fleet. But still, this is not enough across a live fleet. If I tell somebody, hey, I know this issue is happening in our fleet, it's going to corrupt your application, and by the way, it's going to take me 1.5 months to figure out, they are not going to be happy with that, right? So we needed to come up with something better, something that is, again, from an idea, it is, just co-locate testing with the workloads, right? But execution-wise, it's extremely hard to do. It needs very fine orchestration, scheduling, ability to work alongside application without causing a perceptible performance impact on the application. So we did that. I think still now, I think it's one of the largest, silent data corruption test frameworks I feel across like all industry. We are able to reduce test times to the order of milliseconds and decrease our time to coverage to 7 days. That, for detecting something that the hardware has no clue about, and it is happening across a large, globally distributed fleet, and to converge on something within 7 days when application and production are running, it was not easy, extremely challenging, but the teams got to do that, and I'm extremely proud of this. We published a paper around this as well. And every single month, we have 350 million fleet seconds of test time that is running on a live fleet. Again, I don't think it has been like executed at that scale before. So still, we run both methods because Fleet Scanner gives us a lot of opportunistic testing, lot of test time, lot of time to bake systems or clusters before we deploy. Ripple testing gives us a lot of ability to converge quickly on certain fault modes in our fleet. But with all of these, we initially said, hey, we have like 1 defect per 1,000 devices. With a lot more methodology, with a lot more experiences, with a lot more signature of SDCs, we continue to find silent data corruptions in our fleet. I think now it is in the order of 1 defect per 500 devices. And we continue to build novel methodologies, novel signatures, novel SDC detection. But I still am concerned about this area because we don't have a good idea of what is that percentage that we still do not know about. Because our methodology, in the absence of silicon-driven approaches, is a black box methodology. We are approaching it from an application level. We are approaching it from instruction sequences and SDC signatures. We are looking for patterns. We are running it across a live fleet. But I still don't know the depth of that iceberg there. And that really scares me. And I think as a community, it should scare all of us. So just to recap, our journey with silent data corruptions, it has been a journey from the time when we initially started seeing fleet sightings, when we started working with our vendors, when we started figuring out how to debug and tackle this problem at scale. It has been a lot of challenges. It has been a lot of innovation, a lot of discoveries on how these things happen. And also the key thing there for us is how do we get the community involved, right? So in our first paper, I remember very vividly when we were publishing our first paper, there's a lot of pushback against this, right? People are saying, oh, you guys cannot publish this. It's going to open up a can of worms. This is not, at that level that we have seen, and so on and so forth. And I remember pushing very strongly saying, this is something that the industry needs to know about, right? If we do not know that this is the rate at which things are happening in a large fleet. Remember that only very few people have millions of these devices running across their data centers. Only very few people can actually look at the scale of the problem. And luckily for us, after we published our first paper, Google validated with their Mercurial course paper, and then Alibaba published another more detailed characterization paper, which validated that that is the scale at which other people are also seeing this issue. So it is not just us, it is the entire community. It is an actual problem. It is something that needed to be looked at. So there is, from then on, there is a lot more effort on this. We did an RFP with academia. We wanted it to open up to universities. We wanted the best and brightest research minds to contribute to this problem area. We awarded RFP from Meta, and then we partnered with OCP. If you're interested, please check out the OCP server resilience work stream, where we have the STC detection RFP, and we are working with 7 universities. There are 5 universities. There are 7 companies on that. Intel, AMD, NVIDIA, ARM, Microsoft, Google, and Meta are all part of the OCP workstream. Finally, I think we also have a lot of work right now happening on the AI SDC detection, which we will talk about in a bit. But I wanted to give this at the beginning of my talk to show the journey. What does it take for a customer to go into silicon level issues, bring them to the community, do the engineering work that's required to find them at scale, and then open it up for research. It is not a small task. While doing it, it was extremely challenging, but I'm very happy where it is right now. I see a lot of universities, I think 70 plus universities are now working on this. A lot of the community are kind of looking at this problem. So I'm very glad, but we are not done. Remember the tip, the iceberg? I still don't know the depth of the iceberg. And personally, To be honest, and I'll share this with the community, like my teams at Meta wouldn't necessarily want to be the ones finding that out. I'd love to get this community involved in that, size the problem for us, enable like kind of approaches to detect and solve STCs. So trust is important. Please also remember the 2 + 2 = 5 example. Trust, when it comes to computing, is extremely important. Software engineers, programmers, the community that depends on the hardware community to give that trust, we need to hold that at a very high level. So silent data corruption is a foundational problem. It is impacting not just regular compute, but AI compute as well. We'll talk about it. But testing investments across the life cycle are a key to establish that test, and that is why it's extremely relevant to this community here. With that, AI, right? I know everybody wants to talk about Llama and go into the AI large cluster deployment. Like AI has had a huge evolution over the few years. That's probably an understatement given a lot of talks from keynotes to everything happening and a lot of energy in that ecosystem. So whether it's text to image generation, like I said, I use that to generate that picture of me herding llamas, whether it's large language models, whether it is creation tools that people can use across our platforms. AI is in a lot of different places, enabling a lot of different use cases. And Meta has been at the forefront of this AI innovation. Our journey is started in enhancing user experiences, but recently we have open source contributed our large language models back to the community. Llama 3 heard of models from when it came out. It's 350+ million downloads, a lot of tens of thousands of services using Llama on top. And we also recently released our multimodal and the small models, 1 billion and 3 billion, in addition to our flagship 405 billion and 70 billion models. So and there's a lot of security features like Llama Guard and so on. So there's an entire ecosystem around Llama 3. This part of my talk is going to go into what got that to that stage, right? How did we build the infrastructure behind Llama? So for delivering larger and larger models, the compute investments that needs to happen, compute requirements rather, is growing at 7x year over year. That is, I think people saw Shankar's keynote earlier today. It is much higher than kind of Moore's law and growth of predictions and investments happening in this area. With that comes a lot of challenges, right? So we need to have compute working alongside network, storage, software, services, all working together to enable a large cluster that can train our larger models. And then this advanced infrastructure is going to propel us towards AGI. But there's a lot of steps in that process. It is a real challenge of scale. For example, our Llama 3 system infrastructure, which housed more than 15 trillion tokens, ran on 16K H100 GPUs. This pushed our model to new heights, but also pushed our infrastructure to be extremely efficient to serve these models. We had a lot of challenges along the way. This was not as simple as, hey, let's just put the cluster together, put everything together, it's going to work right out of the box, and we're going to have our training model done. The Llama 3 is a published paper. I'll highly encourage the audience to go look at it. There was a very popular table in there that talked about the failures that we encountered when running Llama 3 model, right? So the interruption sources for the model are many. When you're running one large training job on a large 16K clusters, you are going to stop or crash the job for a variety of reasons. Some of the reasons are things like configuration, software issues, network tuning and all that. So network is definitely complex, right? So debugging network issues is extremely complex as well. Configuration issues are complex as well. But you harden them over time. What you cannot escape from is hardware faults. When hardware fails, you necessarily have to stop. You have to detect where the failure is. You need to recover from it, and from a checkpoint, and then rerun the training job. So it directly impacts the stability of that cluster. This is there is a table. I just call out a couple of things in here. GPU is one of the top failing components in there. The DRAM memory is one of the other top component in there. There are SDCs, the silent data corruptions in this too. We'll talk about it in a couple of slides. But the fact being 70% plus of training job interruptions are hardware failures. And there are different ways in which we can test for them, in which we can figure out how to protect our cluster from them. I'll talk about some of them. But before doing that, I do want to call out, why does it matter? Why does it matter, that we have hardware failures? We've had hardware failures. Hardware failures are eventually every hardware system will have failure, right? So, but then this is a very interesting concept about larger and larger models getting trained on larger and larger clusters is that there is a math that works against us in there. So as you build larger clusters, the time that the cluster can stay alive without having a hardware interruption becomes an important constraint. So if you look at a 68 cluster and then extrapolate it to an 100K cluster, there's only going to be 10 minutes of useful work that you can do before there is a crash on that cluster. And that is your time to do useful work, but that's also your time to detect, remediate, resolve, and put in a new host back into the system to take that training job. That is a significant challenge for us. Why? Because think of this like a cluster having multiple hardware systems, and then there is a failure somewhere. I say somewhere because sometimes hard faults are nice because I know that something reliably failed somewhere, and then I can go just swap that in and then run things on there. But not all hardware faults are that way. There are intermittent faults, there are silent faults, and it becomes extremely hard for us to debug them. So the first thing for us to optimize is time to detect, right? We need to be extremely good at detecting where hardware issues are happening. How do you detect things? Hardware can give you signals. It can write to some log. It can give you some events. Or you run tests to detect what is happening wrong with your hardware. All that needs to happen within a short span of time. Second thing that needs to happen is we need to replace hardware with the good hardware. And then we need to restart our training job from a checkpoint and rerun the entire job again. And this keeps happening multiple times for different hardware errors. That's not nice as well, because when we are initially setting up clusters, there's the initial deployment issues. Then we are setting up clusters. These don't nicely happen in kind of individual time periods. These happen at different time periods and so on. So once we make the cluster stable, we have a lot of stable iterations, and we run our Llama herd of models. So overall, why hardware failures and silent data corruptions matter for AI clusters is testing. I mean, the time that we take to test, detect, resolve, and recover is an important first-order constraint for AI clusters. It is fundamentally different than a regular compute cluster. Even a single hardware failure can take down a cluster-level job. So increasing early-stage silicon test and doing a lot of pre-test becomes extremely important for us when it comes to AI clusters. But again, there is a trade-off in there. I cannot take infinite time to make sure my cluster is stable, and I cannot prevent all hardware failures from happening in my AI cluster as well. So there is a very difficult trade-off that we need to optimize for. So finally, silent data corruptions, tying the first part of my talk to AI workloads. A lot of people, I do this because a lot of people come and tell me, hey, why should we care about, AI workloads are so tolerant, nothing is going to happen and so on. I want to dispel that notion. AI workloads do care about events. We published a paper. We showed how many issues happen there. But just to summarize, on training, silent data corruptions are going to cause error propagation that is extremely hard to go back and detect. So gradient explosion, corruption propagation. We have a lot of work in the domain. We have algorithmic fault-tolerant work. We have NAND detection in PyTorch. We have periodic and opportunistic STC detection. So these are all venues where we have talked about or published papers around this. People also say, why should it matter for inference? It really depends on what you're doing with that inference, right? If it is a recommendation or on specific impact to security, privacy, or policy, you need to worry about it. So the difficult challenge for us there is understanding sensitivity of which models is more sensitive to SDC. So we define something called parameter vulnerability factor, which is very similar to the AVF, architecture vulnerability factor, which talks about how different models react to SDCs. And we also have Dr. DNA that was published in ASPLOS, which talks about signatures of SDCs that you can detect for, and how models, certain models are impacted by different signatures. I'm going to give you one example of how we test for some of these things in our fleet. There are different testing methodologies. I won't be able to go through all of them, but this is an example of how we run something called pre-flight checks, right? It's, this is something that enables a large cluster to have more stability. So when a gang of hosts are selected in a particular, for a particular training job, we check individual host with a lot of think of this as simple test, burn-in test that go and check for, hey, is this host ready? Is this host trustable that it's going to be stable for a longer time? And then we replace any faulty devices, we change the host list, and then do a distributed communication check, looking for network. We really need a way to isolate failures before they can happen in the cluster. And we spend a lot of time to make sure a cluster is stable. So we call them pre-flight checks. So given all of the work on AI clusters, none of the problems went away, just the nature of how we look at it changed, and where we need to optimize also changed. Finally, I'm going to talk about the future, right? Meta training and inference accelerators, we are building custom silicon. They are called MTIA. So, this is Mark holding one of our chips. This is really a great opportunity for us. So what was black box to us for a long time is now open. So we have ability to influence things all the way from design, architecture, implementation, down to post-silicon and in production. So literally the entire silicon life cycle is something that we can optimize on. And I'm going to share some areas in here, and we'll talk about what some of the opportunities are. So, but before that, I'm going to give you a couple of early chips that we have deployed in our data centers. So this is MTAA V1. It was a 7-nanometer chip, 25-watt TDP, 65 million flops. And the next chip that we released is a 5-nanometer technology, 90-watt, 103 million flops. All of these are things that are already in our data centers. The chips that we are working on are significantly larger, higher power TDP than these chips, that can serve inference and training at our scale. Again, as a lot of people know in the audience, or probably already know, a silicon development lifecycle, we need to worry about where reliability challenges are going to come from across these lifecycle. We need to put in features early on in the lifecycle. We need to test them. We need to simulate, emulate. We need to do a lot of pre-silicon work to make sure we are able to, timings are not closing, changes from, design, changes, RFCs are coming in, HPM, we need to do some increases, frequency are changing. There's a lot of things that happens in the stages that we need to be guarding against, putting guardrails around. But also, during, bring up validation, we need to work on a lot more areas to do that. So then you go into the system level integration, EVT, DVT, PVT, and then mass production. So there is overall, I would say, there's a lot of things that happen across an entire life cycle that we need to focus on, primarily, with relevance to this community on diagnosis, issue debug, production enablement, and optimization. So the reason I point to all of these areas as opportunities is because we need to be working on all of them, not just one of them. There is no magic bullet in any one stage for us to go figure out SDCs or reliability issues. We need to do all of them. I'm going to just highlight 3 different areas, and I call this rate of change of technology challenge here, because things are happening at a pace at which existing solutions are not able to keep up. I'm going to throw out some statements here because, yes, it's a visionary talk. It's something that challenges us, and I'm sure it challenges community too. One, the pace at which gate counts and power densities and technologies are scaling for the chips that we want to deploy for the AI applications, I don't think emulation is keeping up, right? So we have challenges with capacity, dev velocity. I mean, we expect to run a lot of our AI models and software in early stages. We want to shift left, and when we want to do that, there is not enough that can accommodate the needs for our applications. Second biggest challenge that we have is speed of flight releases. So as things are evolving, becoming more complex, it doesn't mean that we have increasing number of time or months to ship that product. The demand on us to ship products is accelerating as well. So we are shipping things in shorter time on things that are way more complex than before. And that is evident when we are bringing up systems, when we are doing characterization or software enablement. We are able to see this as a huge challenge that we need to tackle and we need to accelerate on. Finally, industry-leading reliability. I've already talked a lot about it. Silent data corruptions. No silicon is going to be immune from things like data corruption. So we need to like kind of provide good diagnostics, good like product life cycle, good control over what we can ship as features after a product has shipped as well. So given that there is an opportunity, like new frontiers for AI silicon from factory to fleet, there are things that this community already works on. There are things that we need to look at in a very different perspective, the customer perspective, right? A person who's deploying the AI models, whether it's training or inference, how are they going to like look at RAS features? How are they going to like run those capabilities in a large fleet? How are they going to do debugs in a large fleet? I talked about our Ripple framework, which is a live in production silent data corruption detecting framework. I have not seen the equivalent of it coming from ground up, right? So we need to think about options or opportunities that can enable these use cases in a large production fleet. So there is a lot more that we can do through the process side also, like yield manufacturing. I think there's a lot of good talks in this conference about some of these things, and also Shankar's keynote touched about a bunch of these. So there's a lot of things that we can do on the manufacturing and yield side as well, looking across the life cycle. And finally, most important, what I want to do over time is to open up a lot of these things for the community to like, build upon, right? So like user space diagnostics, configs, like firmware, how can we do development and, like analytics, things like wear out, time-based, like diagnostics. So there's a lot of things that we can do from, like deployment systems, and we can like kind of, understand how these things operate at scale. So this is another area of opportunity. So the final takeaway for us, the third takeaway on the slide is technology is rapidly accelerating for AI silicon. It is not just Meta, it is happening across the industry. At every layer of the stack, complexity and reliability needs to be taken care of. We have lesser and lesser time to ship things that would have, something that we shipped earlier with a lot more time, the gate count, the power, the TDP, everything has increased, but we are shipping it within those time windows. So we need to have a lot of innovation and testing across the stack to achieve state-of-the-art reliability. Like, I said, I have 1 in 500 STCs. I don't want to see the number even more precipitously drop when we are doing our own silicon. So that is the call to action. That is the, ask from the community. If you need one slide to take away today's keynote, it is the 3 T's of testing for testing AI at scale. Number 1 is trust. There's some fancy, Meta AI Llamas in there. This is, like what I mentioned in the early part of my talk, things like silent data corruptions erode the trust in our community. We need to like really focus on that as an industry. 2, time. AI clusters, time is an important constraint, time to detect, time to resolve, time to recover. So testing time is also very important for us to focus on. It is a large cluster, so we need to figure out how to like kind of distributedly test it as well. Finally, technology. What used to be, like scaling earlier at speeds of releases that we are accustomed to, it is not the same. The rate of change of technology is significantly higher now on the AI silicon stack. So all of us need to like think about how to like satisfy that. So with that, I know I'm a few minutes over, so I'll take questions offline. I don't think we'll have like enough time to take questions here, but I'll be available around for people who have questions. This I want to call out. The team got an Emmy award, Technology Emmy Award recently for our video accelerator. That's pretty cool. Like it's a fancy event with a lot of things. But also, like we are building out a lot of like functions around here. If you're interested to talk to me about it, there is a like code in here that you can go click and it's going to take you to the careers page. But also you can reach out to me, connect with me, and talk with me. So thank you, and I'm looking forward to working with all of you.